Okay, today's lesson is writing Lewis structures for covalently bonded compounds. And this lesson assumes that you know how to do a Lewis dot diagram for an individual atom or element. And if you don't know how to do that, you should review the materials that I've put together in another video tutorial on how to do that. So this assumes that you know how to do that. This also assumes that you're familiar with the covalent bonds and things like that, so we know what the covalent bond is, a sharing of electrons between the two. So if you are familiar with both of those and you're ready to move on, our first general rule for writing a Lewis structure with covalent bonds is to select a center atom. The center atom is going to be the one that has the least electronegative negativity, and it's usually carbon if carbon's in the system, but it's never going to be hydrogen. So the least electronegative material, where hydrogen is not ever going to be the center atom. If you only have 2 atoms, you're never going to have a center atom either, right? You need to have at least 3 plus atoms to have a center atom. And even if you have 4 atoms or 6 atoms, sometimes you're not going to have a center atom either, right? Generally, it works best with an odd number of atoms, but not always. But sometimes this is just trial and error, and you're going to have to try out things to make before they come together. So once you've selected your center atom, you're going to put the other ones around the outside of it. So let's just call this our center atom here. And then let's say we had 3 other atoms involved. We're going to put them, in around here. And I like to do it this way. If I have 2 atoms extra, I put them in a line. So let's just do another one here where I'm going to make these a triangle. So these are my 2 other atoms. So they're going to be in the line with the center atom. If I have 3, I generally put them in a triangle. And if I have 4, put a different color. If I have 4, I generally put them in some type of a box thing. And this isn't a hard, fast rule. I just like to do it this way because there is some symmetry when you do the bonding in real life. And this kind of gives you an idea of the symmetrical stuff that goes on in real life. So I kind of do it that way. If you had 5, you put a pentagon and things like that. It's just to help a visual. There's no real... It's not correct or incorrect. It's just a visual for me to do it that way. And some people say, well, you really shouldn't do it that way, or that doesn't make a difference. It doesn't really, but it helps me visualize spatial things. And then what you're going to do is you're going to draw, let's say back to our center atom again, and let's say I only have 3 things here. You're going to draw a single bond between each one of the pendant ones and the center atom. And I did that. And remember, a covalent bond is represented by a dashed line or a small line segment. And so I did that there. And then the last thing, the next thing we're going to do is we're going to count the number of valence electrons that each atom brings into the system. So let's just look at that real quick. If we have CO2, so we have C, and then there's 2 oxygens, so there's an O and an O. Each one of the oxygens brings in 6, and then the carbon brings in 4, so we have a total of 16 electrons that it brings in. All right. And if we need to add or subtract electrons because of a charge, like a polyatomic ion, we're going to have to add electrons here or subtract electrons from the total valence number. Right. And I'll get into that in a second when we do that as an example in the back page. Right. And from each bonds in the skeletal structure, which we've drawn here with the lines, you're going to subtract 2 electrons from the total valence electrons. So let's go back to our little quick example here. Let's say we had total 16 electrons total, and we had 3 bonds that we already made. So we're going to subtract. Each bond has 2 electrons, so we need to total 6 electrons total. So we have 10 electrons remaining to put someplace. And then number 6 says, using the remaining electrons, we're going to complete the octets on the terminal atoms by placing pairs of electrons around each atom. And the key thing to take away from this is we need to replace things in pairs, right? Not individual electrons. Each atom complete the octets in pairs. So pairs of electrons on each atom. And we always go to the octets with the most electronegative atom first, right? Because they're going to always want the electrons more so than the other electrons, right? And if you have, let's say you had carbon tetrachloride with CCl4, you would kind of space out the electrons around all four of those as you move around, and I'll show you how to do that in a minute. And then if you have any remaining pairs, you're going to put them back on the central atom. And then if the central atom is fewer than the number of electrons it needs to complete its octet, then you're going to move some of the electrons off the octets on the outside atoms into this region for the center atom. You're going to share those. So we create double bonds and triple bonds and things like that. And I'll show you how to do that in a few minutes. So those are basically the rules that we're going to follow. And if you do these rules, 99.9% of the time, you're going to actually get the structure the first time. Okay, so let's start with the simplest one first. And the simplest one has no central atom, and it's going to be the HF molecule here. So let's look at that first. So we have two elements here, H and F. So we're going to first draw our elements. Here's my H, and then my F. And I'm going to put my bond between them, and that's going to be represented by, I'm going to represent that by a red line. Okay, and then I'm going to now count how many electrons that each one of the atoms brought in. So we're going to do that up here. So the hydrogen brought in 1, and the fluorine brought in 7, and then we'll add them together. So we have 8 total electrons. And on top of that, so now I've got 8 electrons that I have to account for in my final structure somehow. So now I'm going to subtract away the number of electrons that are already in a bond. And since we have one bond, we're going to subtract one pair of electrons. So we have one pair of electrons. So one pair of E's that equals 2 electrons. And if we subtract that, we have 6 electrons that we have to account for. So far, so good? Okay. Now, the last thing we need to do, the second to last thing, or one of the last things we need to do, is we need to start putting the remaining 6 electrons around the atoms in pairs to satisfy the octet. So let's start doing that real quick. So I'm going to start with my most electronegative element first, and that's going to be my fluorine. So I'm going to put a dot here and a dot here. Let me erase this real quick here and move this a little bit down. All right, so that I'm going to put them here, H, and then F, and I'm going to make that red bond again so that people know. Okay, and now I'm going to start putting my dots around my electronegative one first. So here's my first dot. Here's my second dot. And remember, they have to go down in pairs, so there's pair 1. Here's pair 2. And then here's pair 3. So I've placed 6 dots, or 3 pairs. I don't have to place any more dots because I've accounted for all 6 electrons, right? So now we have to check. Let's check that we've done this right. So we're going to look at the electrons around the fluorine first. Right, so those are all these electrons that are bonded to the fluorine. And let's count them. So we know that this bond here has 2 electrons, right? Because each electron pair has 2 electrons, and they're being shared. So here's 2, 3, 4, 5, 6, 7, 8. So the octet is satisfied for fluorine. So we have 8 electrons around fluorine. And now we're going to look at all the electrons associated with the hydrogen. And we know that hydrogen can have a max of 2 electrons. So let's see if they have them. 1, 2. Remember, each bond is 2 electrons. So the octet, or the duet around hydrogen, is satisfied. So this this molecule is now properly written in a Lewis dot structure, right? I know where all the electrons are around the H and F, and I know that all the electrons, all the unpaired the unbonded electrons in pairs are around the fluorine, and there's none around the hydrogen, and I know that there's a pair of electrons between the hydrogen and fluorine. So far so good. Let's go to our next simplest one, which will be the CH4 molecule. All right, this one does have a central atom, and based on our rules, remember that the hydrogen cannot be the central atom, and carbon often is, so it's fortuitous that the carbon is going to be this one here. So we're going to put our carbon here, and then we're going to put our H's around each one of the sides, the four sides. Okay, and we've done that, and then our next task is to put a bond in between each one of them, and we've done that. And then our next task is to count how many valence electrons that each element brings in. So let's do that real quick. The carbon, there's one carbon, and that's going to bring in 4. Remember, there's 4 electrons around carbon. And then there's 4 hydrogens, so there's 4 times hydrogen, and each one of those brings in 1, and so that's going to equal 4. So we have a total of 8 electrons. Okay, and then now we know that we have 4 bonds around the carbon, right? So we have to subtract away 4 times 2, which will be 8 electrons, because each bond has 8 electrons, 2 electrons, there's 4 of them, so we have no electrons that we have to account for as far as unbonded. So all the electrons are now occupied in the bonds. So this is the correct structure for CH4. Okay, and so that's the correct structure for that one. And you can see that there are no pairs that we need to worry about elsewhere like we did on the previous one, because all the bonds occupy all the things. And just to double check, let's look at all the electrons around the carbon, right? We have 1, 2, 3, 4 bonds. Each bond has 2 electrons, so there's 8 around the carbon. So that octet is satisfied. And if we just look at one of the hydrogens, since they're all the same, there's 1 bond between that and the carbon, and there's no unbonded pairs. So there's 2 electrons there, and 2 electrons occupies or satisfies the duet, and so this structure is accurate. Okay, now we're going to go to do one that has the next step up as far as complexity, and let's do the one here, CO2. Okay, and we know that the least electronegativity one is this one is carbon. And so the others, the O is going to be the most electronegative, so it's going to be the outside. So I'm just going to quickly draw this, what they look like, right? And let's just put that in the center. And to save time, I'm going to tell you that the carbon brings in 4 electrons, the oxygen brings in 6, and then the other oxygen brings in 6. So we have a total of 16 electrons that we have to accommodate, right? And so, because if you add these together, you get that. And then now we have 2 bonds, so we're going to subtract away 4 electrons because each bond has 2. So we need to accommodate for 12 electrons. All right, so let's just write that there. That's our 12 electrons that we have to accommodate for. And let's just erase some of this other stuff here. We don't need this anymore. We just got to know how many electrons we've got to keep putting around this. So I've erased this. And now, let's start putting our electrons around where we need to put them. So since we have 2 opposite oxygens, there's none of these are any more electronegative than the other. So what I'm going to do is, I'm going to put 2, I'm going to just alternate from each side. So I'm going to put 2 here first, and then I'm going to put another 2 here. So I've done 4 so far. and then another 2 here, and another 2 here, because I want to make them equal because there's no preference on each side. And then I'm going to put another 2 here, and then the final 2 I'm going to put here. This is a dot, not a, sorry about that, that's a dot there. Let me just erase that to make that a little bit cleaner. This is a dot. Okay. And now, so let's look at the thing. So we have got 12. Let's make sure we had the 12 that we've added, right? Even though I can see that we did 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, good. And then we know we have 14 and then 16. So we have all the electrons counted for because we needed to add 12. We had 4 more, so that's good. So let's erase some of this stuff real quick. Let's erase some of this, and we don't need the 12 anymore. Okay. So now we have to do the following. We know that when we do this, we need to make sure that we have the correct octet around each one. So let's look at the oxygen first. And since they're both the same, we're just going to look at one. So here's my octet for the oxygen. And these are all the electrons that are bonded to the oxygen. Right? And we can count them. 1, 2, 3, 4, 5, 6, 7, and 8. So those check. And then again, this is the same on this side. So these would have 1, 2, 3, 4, 5, 6, 7, 8. So again, check. And now let's look at the carbon ones. Remember, we have to include the whole bond for the carbon right in the middle here. And we have 1, 2, 3, 4. Okay, so carbon does not have the proper number of electrons to complete its octet. So what are we going to do? Well, what we're going to do is we're actually going to do this. We're going to use these electrons here, and we're going to bring them down and make a bond here. And since we have to do it on this side, we're going to have to do it on the other side too, because remember, this had 4. I can bring 3 and 2 in here. I'm going to make sure that things are equal, so I'm going to bring the other 2 in here like this too. And you can do that because these electrons are all valence electrons and available for bonding. So even though that they're associated with the oxygen, the carbon needs them to make its octet, so it's going to pull them in. So let's just do a little bit of erasing and rewrite this the proper way. All right. Let's just do a little erasing here and rewrite this the proper way now. So if you do that, and you properly do this now, you're going to have C double bond, right, because those electrons came down and they made a bond. And then we're going to put our remaining electrons back to where they were. And again, it doesn't matter where you put them, right, as long as they're in there. I just like to put them on the opposite side. Okay, now let's count the octet around each one of these, right? This still has 8 electrons associated with it. Let's just to make sure. 1, 2, 3, 4, 5, 6, 7, 8. Again, if we look on this side, 1, 2, 3, 4, 5, 6, 7, 8. And now let's look around the carbon. 1, 2, 3, 4, 5, 6, 7, 8. So that checks. So that is going to be your correct Lewis structure for carbon dioxide. All right, and I'm going to do one more with you, and then I want you to do the other 2 by yourself, and then we'll come back and check them. The last one is going to have a different set of different challenge to it, and I'll show you what that is in a minute. So let's look real quick. I'm just going to quickly draw. You should now know how to draw these. You're going to put the central atom. In this case, it's going to be the nitrogen. And then we're going to surround it by the 3 hydrogens. Right? And then we're going to put our bond in. And we know that I'm just going to quickly do this to save some time. The nitrogen has 5 electrons, and each hydrogen has 1. So we're going to say 3 electrons from all the hydrogens. Okay, so we have 8 total. I'm going to put the 8 total here, and then let's subtract our number of bonds, and then we have, here we go, 1, 2, 3, 4, 5, 6. So we have 6 electrons in bonds, so we need to account for 2 electrons. We need to figure out where to put 2 electrons. So I can erase all this now. All right. And so we need to put 2 electrons. Well, we know we can't put them around the hydrogens because we're not allowed to add any more electrons around hydrogen, because that would exceed its octet or its duet, right? Because there's already 2 here, right? So if we draw a little structure here, that has 2, and this has 2, and this has 2, so we can't put anything around there. And if you look at the nitrogen, that has 1, 2, 3, 4, 5, 6. So what's going to happen is these 2 electrons, if you remember back to rule, I think it's 7, saying that the electrons must now go back towards the central atom, and so we're going to draw 2 electrons on the nitrogen, right? And now when we do our structure here, we have 1, 2, 3, 4, 5, 6, 7, 8. The octet around nitrogen is satisfied, and the duet around hydrogen is satisfied. So this is the correct structure for ammonia, right? And you need to put those lone pair in there, otherwise the structure is not accurate. Just like you need to put these unbonded pairs of electrons around each oxygen in the CO2, or that's not an accurate structure. All right, so now I want you to do these 2 here by yourself with the rules we had, right? And in this one, you're going to have to add 2 electrons, right? Because it says 2 minus. All right, so let me, it says add 2 minus. Add 2 electrons. And you're going to have to add that to the total structure, so don't forget to do that when you're doing that. Okay, so stop the video, copy these down, and I'll come back with the answers. Okay, so I've written in the answers to the 2 problems, and let me just go over them real quick. This structure here with the CO is the only one that's going to give you the proper number of octets around both the carbon and the oxygen. So here we go. You can do the quick count: 1, 2, 3, 4, 5, 6, 7, 8, and then 1, 2, 3, 4, 5, 6, 7, 8. So both octets are satisfied with this structure. And you might have tried to write it another way, but this is the only one that satisfies the octets for both of them. And on the last problem, you had to add 2 electrons to your total valence electrons. Remember, it's the valence electrons that you brought in with each atom, plus any electrons that you either have to add or subtract. So you had to add 2 more. And when you do that, you need to accommodate for 18 electrons after you put down your 6 electrons for your bonding. Remember, each one of these oxygens normally brings in 6, so it'll be 6, 12, 18. The carbon brings in 4, which is 22, plus 2 more is 24. And if you add up all the electrons now here, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then 12, 14, 16, 18, 22, 24. So this structure is accurate, and you need to put 2 minus. Now, one thing to remember is, and you're going to learn a little bit more about this in another chapter, is this thing called resonance. It doesn't really matter where you put this double bond, right? It could have been down here, or it could have been over here. There's no real. This atom here, this top atom, doesn't necessarily have to have this double bond, because you could have just switched this whole thing around and had it to be down here or over here. There's no real correct way to write this. This is not more correct than if you had it down here or down here, and I'll talk about that later in another video. But you do need to put this bracket around here, and then the 2 minus, or the -2, depending on how you want to write it, to show you that it's an ion, right? This is CO3 minus 2 is the carbonate ion, so you need to write that. Okay, I'm going to have another thing on the next page with some more examples of practice if you want to work on it. If not, this is the end of the technical part or the description part of the video. I'll have another part of the section on the next one. You can write the answers, and then we'll go from there. Okay, here's some more practice for you. So if you're still uncomfortable doing it or still need a little bit more work, try these first, and then if you're still uncomfortable after doing this, you should come find me. But here are 6 more problems here. They each have some level of difference between them to highlight all of the rules that we need to do, and you should go from there. And now what you're going to do is you're going to copy these down, stop the video, copy these down, work them out, and then start the video again, and we'll go from there, and I'll have the answers. So stop the video now. Okay, so I've written you down the answers. Now there's a couple of things you got to make sure you do when you do these Lewis dot structures, and I can't stress this enough. You have to make sure that you have all the dots around each particular atom so that you can complete the octet. And there's a lot of folks, and I'm going to give you an example right now. So if you've checked these answers, this thing here is that little this little doohickey thing here is not there. It was just a pens thing. So it should be 3 bonds here, 1 bond here, 1 bond here. But let me give you an example of something that is not the correct way to do when you do these. So let's just pick water here, for example. This is water's down here. Right. I'm going to draw you a structure where you're not supposed to do it the way it's not supposed to be done. And I'm going to put that in blue. And so we know their central atoms oxygen. And we're going to put the H here and then the other H here. And a lot of people do not, they do not put the other 2 dots here. They omit them. So they're supposed to be dots here, right? Because they need them for this octet. But a lot of folks are lazy, or they will learn the wrong way, that they can just leave it like that. And that is incorrect, because what happens is if you draw your circle around the oxygen to see how many how many electrons are bonding there, there's no account for those unpaired electrons. So you're going to count only 2 and 4, and that's incorrect. So you need to have all the dots around all the pendant electrons, and then the center electron if they require it. So a common mistake is to leave those dots off, and that is incorrect. Right? So that's an incorrect way to do that. So if you manage to do all these correctly and you did it right, give yourselves a gold star, and I think you're well on your way to doing that. All right, that ends the lesson.